All right. I think it is almost time to start. Let me welcome you all to the next edition of Mython Times. Thank you all for coming and people online for joining. Because I see quite a few new faces in the room, I'm going to start with a little bit of organization. We'll first have the talk. Please, if you have any questions, keep them until the end of the presentation. There will be space for you to ask them. And also after the talk, there are refreshments ready, and we would be happy to talk to all of you. But so without further ado, today's topic is autonomous driving and driving formulas. We have three people, David, Marko, and Roman from the Faculty of Electrical Engineering from the eForce team, who are working exactly on self-driving formulas, if I'm correct. And I'm going to let them tell you more about the competition they are taking part in.
Yeah, thank you. Hi, everyone. So I'm going to go first. And first, I want to talk about and describe to you what the whole competition is about, what we are doing, what is our team. So first, what is Formula Student? Formula Student is a worldwide competition that started overseas. And its main design was to make a competition where talented students from colleges, universities could come up together, design, build, and then compete with the formulas, which were firstly combustion, and then in the 21st century, they started to be even electric, and then autonomous. There is a map of the all competition taking place worldwide. As you can see, it's spread across the whole globe. But the most of the competitions happen to be in Europe because there are, from the 800 teams that are registered in the world, more than 500 are registered in the Europe only. The newest addition to the competition was the driverless autonomous category, which was added in 2016. And from that time, it began our main goal at CTU in Prague to actually compete in this category. So from the first year, we were starting to develop the autonomous car. So we are one of the first team with TH Zurich and along other European teams that are taking part in this competition. And that's what we specialize for, and that's what we are the most proud of. Yeah. This is the competition cake because it's an engineering competition. It's not typical competition as you could see in motorsport like Formula One or NASCAR or other competitions, because the red part of the cake consists only of static disciplines, engineering design making the discipline with the holding most points, and that's jewel of the whole competition, because in this discipline we have to come up from the judges, which come from various firms, automotive firms, science, other firms that are like top-notch firms or other universities, and we have to defend the design. We have to show them that our design is most unique, is some kind of next generation revolutionary design, and we have to do it with not only present it to them, sell them to them, but we have to have the validations, testings, everything ready to actually defend it like we would defend our theses or other subjects. Before we can go to the track and actually compete and race in the competition, we have to go through a big number of scrutineerings because safety is first, and the rule set is really strict. So if we go on a week-long race, 4 to 5 days, we're only in the pits, and we have to go through electrical, mechanical, autonomous scrutineering to actually to show the judges that we have a rule-compliant car that we can race. Then we have to pass the brake test, rain test, that we can go race in the rainy conditions, because the cars are electric, so they're holding AccuPacks which are developed on the faculty. These AccuPacks are not stock; everyone designs them, so it is a safety hazard to actually get racing without checking the rules at first. Now we can go to the. I will mute it. So we can go to the particular disciplines. The first one is acceleration, just testing the acceleration of the car. So 75 meters long straight, and there's 75 meter braking zone, which this particular discipline is both piloted and autonomous. Then we have skid pad, which tests the lateral velocity of the car and the ability of the car to handle lateral force. So it consists of two circles where we go two circles to the right and then two circles to the left. The second circle is always timed, and then the average is taken, and that's the time we get. And from this year, we've managed to surprise a competition, and we have a video, which I'll show it to you, where we are really proud of what we did achieve this year. This is the German competition, the most prestigious ones of them all.
42. Look what car it is. It's beautiful. Finally, a non-black car. Of course, now is one of the opportunities for Prague to prove that 42 is the answer to life, the universe, and everything. Pretty good setup. Very clean hand size. This looks quick, but it's very stiff. 5.22 of the right. Holy shit. Cheering on from the safety stands. So let go. 5.03 on the left for a total of 5.03. Wow. Very, very close to that sub per second. They are up there with the man bars. He took fourth overall so far. It's crazy.
I will speak about a little bit later why this spectacular moment was important for us. And the clarification for the non-black cars is because a lot of cars don't use the livery that we are, like the whole side of the car livery, because they're saving grams to actually be lighter, to move faster. So it is really unique to have like colorful car. They're black because the monocoque is made of carbon fiber. And the last two disciplines are autocross and track drive. Autocross is a hot lap, or as we would say in other motorsports, a qualifying lap, where we set up the time, and then that's the order of when we will start at the track drive or endurance, which is a piloting competition. The important part that it's an unknown track. We do not have the acceleration. We know how it look like. They're set in stone, and we know what we are going to race on. But the autocross and track drive, they're unknown. We don't know where we're going. So first we have to orient where the car will go, where David and Roman will tell more about it. This is the video from testing from, I think, summer testing, yes. Now that I've handled the competition overall, I'll briefly go through our car and our history. First, this is photo of our car in Czech, in the most. We were two teams in our university. The orange part is the electric part, where we've built electric cars only. And from the year 2019, we've joined the competition of driverless category with first driverless car. In 2022, we've managed to merge the cars into one car. So the car is capable of piloted and autonomous driving, not at the same time, but it can be changed in, let's say, 5 minutes. The left part is the combustion part, which unfortunately is going away because the competition is more into the electrical and autonomous state. That's why we have decided for last year to join the both teams into one team, and to have only one team who is going to build electrical autonomous car. We did manage to do it amongst all the complications that we had to encounter about joining the team, like management issues, concept issues, everything. And we have ended top 5 in the world. And the skid pad was the first our first discipline where we were compared to the top teams in the world. So this is where we did show that we are capable of racing and capable of racing quick in the autonomous category. Now I'll take you through different parts of our team and what they do. Firstly, we have chassis. They do the main concept of the car. They're responsible of building the composite monocoque and integrate all units into the car physically. And then they simulate and design mainly the safety for the driver. So when the driver crashes or there big force is applied to him, the car doesn't just loosen up. The next one is drivetrain and suspension. These two groups are coherently linked because suspension is doing everything from the monocoque to wheel hub, and the drivetrain is responsible for the engines in the wheel. Unique part of our formula is that we have a true 4x4 drive, four-wheel drive, because we have engine in every wheel hub. So every wheel hub on the left has one engine. That makes us capable of doing the true torque vectoring and vehicle dynamics like none of the other cars. And then we have electronics and aerodynamics. Aerodynamics is a group that has doing the body work around the chassis and is responsible for generating as much downforce as possible. That's why it does not look quite like Formula One and other cars, because we are racing in low speeds. The top speed of our car is 120 kilometers per hour. So the area of which we have to generate downforce has to be much greater in the ratio of the rest of the car. That's why it looks a little like a box. And electronics is responsible for low voltage and high voltage systems. So the big orange box below the legs of the pilot is an accumulator. In the back we have our own controller, cooling units, even the main computing device for the category, and that's everything that electronics do. And now the part of the team that we all three are a part of is the autonomous part, and I'll let Roman tell you something more about development.
All right, so hello everyone again. So I'm Roman, and I'll be speaking about the development of the autonomous part. So fun slides, to start with. So what makes us special? So in what sense? Well, in the sense that when we are at a competition and a competing team, comes to us and they ask us, how our car works, how we solve different problems. There is, several, kind of things that surprise them. So first one is that we are actually quite a small team or a small autonomous section. We've been consistently 3 to 5 people at one time over the years. Second, that's a big one, is that we are vision only. So typically all the good teams, they use typically like one very good, very expensive LiDAR. We are cameras only. Another thing is that we actually have only a single camera. So that also surprises them. And maybe the least, that maybe you wouldn't expect is our software stack and our development approach is, quite unique and, quite different to how, other teams approach this. So that's what I will be, talking about mostly. So developing a driverless formula. So, well, what you get? So typically you start as part of an electric, formula team. So they give you like a piloted EV formula. It has, CAN buses that have some, electrical control units on them. So you can, read messages from the CAN bus. You can send messages to it, assuming it has a steering motor and, CAN controlled motor controllers. And well, that's kind of the catch of the competition, is that, as you guys noticed, we built a new car every year. So if you are the autonomous group, you kind of only get, 1 to 2 weeks, sometimes you get 4 weeks before, your first competition. So you don't have much time, to test your algorithms and to do a lot of real-time testing. So what do you do? Well, so you have to pick your sensors, right? Your cameras, LiDARs. You have to pick a computer that you will put, in the car and that all the autonomous systems will run on. And you have to develop your algorithms, right? So it's the typical, vision, planning, control split. But there is something missing. So usually most people would stop with this. It's like, okay, I have my hardware, I have my software. Let's race, let's win. But well, what have we forgotten? So well, maybe you should focus on designing your software architecture. What will be your inputs, outputs? How will the microservice diagram look? What will be your testing infrastructure? How hard is it to run a virtual experiment? Do you have a virtual twin? How convenient it is to run such an experiment? Do you have automatic validation? If you change something, will things break or will they not? Do you have good, tools for diagnosing, your car when it fails, on the racetrack? How long does it take you to identify, why it happened? So maybe let's talk about, different development philosophies. How to approach, such a, robotics or self-driving cars problem. So, well, the first, development philosophy that, maybe most people go for at the start is the performance first. So, they say, get 5 cameras, get the LiDAR. The more sensors you have, the more of the world you see. So that must be better, right? They say, oh, let's get, all the computers. More computers equals more flops. They say, oh, let's use this, latest deep learning, depth anything for cone localization. They say, oh, look, there is this new ultra-realistic simulator that just came out. And, these things make sense. But maybe if you, try to go all in on all these fronts, maybe, you'll go mad. And it will be hard to, make sense of all this. So there is another development philosophy that maybe, we've kind of gravitated towards over the years. And that's, development experience first. So maybe the question you ask, first is, how do we run virtual experiments, fast and conveniently? Do they run on everyone's laptop, or is it an issue? Is an extra sensor worth the complexity adds? Maybe you can add, 3 more cameras, but suddenly, you need, multiple computers, so on. How do we know a change to the system, didn't make things work? That's a big one. Right? If you have complex systems like this and, you think you maybe improve the system by making a change, but how can you be sure? So I'll go over some, typical pitfalls that maybe teams usually go through. So the hardware pitfalls, the one I alluded to several times is getting more than one sensor, at the start. So they will be like, okay, let's get 3 cameras and 1 LiDAR. And that's actually what happened to us in our first year. We had more sensors than we do have now. So, our solution is to, get a single camera, and the general rule that we follow is if you can't make it work with 1 sensor, then, adding more sensor won't save you. And similarly, getting more than 1 computer is a typical, another pitfall. So people will say, let's get an extra computer for each sensor, and run a neural net there, for every camera. Or they will go the other extreme and will be like, oh, let's get a 10-watt embedded chip. While these ideas are great, they probably will slow down your development so much that, you won't really go anywhere. So our solution is we have a standard Zotac mini computer. It has an i7 processor, NVIDIA GPU, runs Ubuntu, very nice to work with. Again, can't make it work with a single computer. Buying more computers will not save you. So now to software pitfalls. The first one might be a bit controversial if you are a robotics developer. So there is this thing called ROS. It's like the most popular robotics framework. It's an entire ecosystem. Basically, every robotics company uses this, and it's great if you really know your way around it. But if you are starting, it can be very overwhelming. And so for example, it has 2 major releases, ROS 1, ROS 2. Each one has like 10 different versions. Each of these versions runs only on a particular Ubuntu version. And suddenly, when you adopt this framework, down the line, you might realize, okay, now all of our members need to run, Ubuntu 2018 because our, sensor runs only this ROS package and so on. Also, people always go for the, hottest, most complicated, simulators, which, maybe are great, but maybe they are overkill for the task at hand. So our solution, this is like what surprises all the other teams is that, okay, our solution is build everything in-house for our specific use case. Another, big software pitfall is, I call it spaghetti microservice architecture. So they are like, okay, everything that is a function will get its own process. So vision is a separate process, planning is a separate process, controls is, state machine is, and maybe these people they don't think about what really makes sense. So our solution is, okay, ask what is the minimal number of processes that we need to run our system, and maybe organize processes based on state and not on functionality. Okay, so finally, to our stuff. So we have developed something which we call BROS. It's our autonomous system. You can see there is a screenshot from GitLab. It's around 2,000 commits. It's developed natively from scratch in Python. It contains the microservice architecture of our system that runs on the car. So processes are handled with multiprocessing library, which is the native process handling library from Python. Inter-process messaging between the processes is handled with the 0MQ library. It contains logging and logging visualization tools. There is a real-time simulator and a timeless simulator. Integration and scenario test suite, and a benchmark and evaluation test suite. I'll go through all of these. So first, the microservice architecture. So this is the simplest diagram that kind of demonstrates what an autonomous system is. So there is the car and the world, and you get readings about the world through the CAN bus. You can read messages from the CAN bus, and you can see with your sensors. And then you can control the world and the car by sending actuator messages to the CAN bus. So this is just the microservice diagram of our system. So not to dwell too much on it. There is it's very simple. There are the input-output nodes. The input processing nodes on the left. We have two CAN buses. We have a camera. They are each processed with their input processing node. Then there is the mission node, which is the main, decision-making node, which has all the information, and it kind of decides, okay, how fast should we go, where should the car go, and so on. And then at the end, there is the motor node, which does the low-level control, and then sends the actuation commands to the back to the CAN. Okay, so let's talk. Well, when you have a microservice architecture like this, so how hard is it to make a simulator? So again, if you think about this, very simple diagram, you basically just need to replace the car and the world with, a separate node that kind of can simulate the CAN communication and somehow simulate the sensors. So again, we've written a simulator. It's natively in Python. It simulates the CAN buses with something that's called virtual CAN. So in Linux kernel, there is this, network interface that you can create called virtual CAN, which just lets you simulate CAN networks just on your laptop. So that's great because it means that the system, it can run just as it would in the car, with the CAN communication, all the, electrical control unit messages on your laptop. Except for vision, we've done like a smart, we found a smart way how to bypass this. And it, it runs, on everyone's laptop, so it's very convenient. Everyone can run experiments and, validate that the system works. Yeah, so that's the advantage is seamless integration. So again, they give us, the build car like 3 weeks before the first competition. And, most teams that don't have such a simulator, they have to kind of sit around the car and try to debug, okay, why isn't the CAN reading working and so on. We do all this, way before just on our laptop and then just put the computer inside the car and everything works on the first try. So one interesting thing is that the simulator is 700 lines in total. There is a GUI file that has 300 lines. There is a state.py that has all the vehicle dynamics and the track, all the cones and so on. That has 200 lines of code. And then there is the states to CAN, which just translates the state of the world into the CAN messages. So we might be like, okay, so it's 700 lines. How well can this work? How will it look like? You would be surprised, with like these many lines of code. If you try to do it right, you can really, build something useful. So this is how it looks like. It's specifically built for our use case. You can see there is even like cone collisions. There is some, information boards on the left, which give us, the speed of the car, even like the state of the of the different nodes and so on. Okay, So that was great, the real-time simulator, but after a while, you realize that running simulations in real time is maybe not fast enough for you. And if a mission takes 1 minute, then you have to wait 1 minute for it to finish, and you would want to get faster. So if you think about what is like a process or a node in this like microservice context, so our definition is that it's a class that has a loop function, and that has some arguments and like how much time has passed since the last time it was looped. So you can run it traditionally as a process. So an example would be you have an image processing node, and the loop function is called each time a new image comes from the camera. Right. So that's the real-time way. But if you set up your abstractions right, you can run it in a timeless way. So the arguments and how much time has passed is simulated, using like your simulator basically. So you run a step of the simulation and then step in the node and so on. So the advantage of this is that it's faster than real time, and it's also what I call it's containerized, so that it's deterministic and it runs on a single process. So that makes it sometimes when you have simulations that are multiple processes and so on, it's kind of hard to get determinism. But if you do it this way, suddenly you can it's way more ideal for validation and evaluation, because with like multiple processes, you sometimes run, okay, this guy has a slow computer, so this node was running slowly, and so on. So anyway, we wrote another GUI for this. It's very like simple, but it's maybe easier for running experiments and to know what is really happening. So there's like the global view and the local view. I'll play a video of it later. And maybe just to showcase that if you have your code abstraction set up right, maybe adding all this functionality takes maybe 50 lines of code. Yeah. So again, this is how this tool looks like. Yeah. So in the top left, there is some readings about the state of the car. There's visualizations of the path planning, and so on. It's very nice to work with as a programmer. It's like a matplotlib object that's exposed to you, so you can draw anything you want specific to your algorithm. Right. So when you have this, you can run all kinds of evaluations, because you can suddenly run a lot of experiments at scale. So you can do grid searches for parameter settings and so on. So one fun evaluation or benchmarking thing that we do is you can kind of find the optimal speed set point by just binary searching it. So you define your lower bound and upper bound of speed, and then you let the car loose in the simulation. If it drives off track, that's a fail. If it finishes the lap, that's a success, and you adjust the speed interval based on that. Right. And when you have this, it's kind of just asking you to just put it in CI and have it run after every commit. So we also do that. We have extensive suite of scenarios for each of the disciplines, for acceleration, for autocross, and so on. And this really kind of helps you not to break things and have confidence that the system will work, because sometimes changing things and not having this is just a nightmare. Right, and the last thing, of course, logging and visualization. So of course we wrote our own logging system in Python. Not much to say about it, right? So it uses Pickle for serialization and of course append write, so that when you log a message and the car would like run out of power or something, the logs aren't corrupted. And then we have what we call log to video. It takes the log files and generates the MP4 file for visualization and doing diagnostics. So here is like example of how the log visualization looks like. So there is 4 different panes. In the top left, you see the image frame. In the top right, there is a bird eye view, local car frame. And then in the bottom left, there is the global world frame, where you can see the mapping algorithm working. And then in the bottom right, there are certain like metrics that are important to us for diagnostics. So first is the frequency of the different nodes, making sure nothing is lagging behind, everything is, running at the right speed. Then there is the, speed of the car, like the set point and the actual speed, and then the steering and steering set point and actual steering angle of the steering wheel. All right, I'll give it to David.
Hi everyone, I'm David, and together we'll look at the algorithm stack. What we've talked so far about why we do it and how we do it, but we haven't said, what we actually do, what we actually use to control and drive the car when it's on the track. We can split this into like 4 separate functional blocks. First, you get the image from the camera, right? We discussed that we use the camera sensor. This gives you some sort of perception of the environment. Then you have to map out the track, localize where you're actually driving at the moment, and you have to plan where you want to go next. And then you have to process this into some sort of actual, physical controls for the car. So when we send the CAN message to the motor controller, that tells it the car how much to accelerate, how to brake, where to steer the steering wheel, stuff like that. So let's start with the vision algorithm, or like the vision approach that we take. As Roman mentioned, and Marko as well, our approach is quite unique. All of the major, most successful teams use just like a big LiDAR, and these LiDARs have quite a bit of disadvantages. Yes, their performance is really good. They are very accurate and they can see really far, like 70 meters, but they are very expensive. They are heavy, they consume a lot of power, and they are slow. From a LiDAR, if you want really good measurements, you get them like 10 times a second, maybe 15. With a camera, cameras, they have like 30, 60, 100 frames per second. So you can get new information about the environment much faster. LiDAR also doesn't have color. You can like estimate some sort of reflectivity, but there's no true color. With the camera, of course, you get a colored image, and this is much better for like deciding what is the actual cone, what is the track, what is the barrier, what are people. It's as little ambiguous as can be, and there are some like construction and engineering advantages to using a camera. It's very light. It consumes basically no power. It's very cheap, and there are no moving parts. Like right, with most LiDARs, there is some sort of spinning mirror. This is fully solid state. Okay, so use a camera and it's good, but how can we actually extract the perception from the camera? So to illustrate the problem that we want to solve, you get an image or 2. We have 2 lenses, but so far we're using just 1. And what you want to get is a map of the cones that are around the car in some sort of metric coordinates, right? So we want to know that the blue cone is 2 meters to the left and 3 meters in front, something like that. And how do you do that just from the image with the camera? You can take multiple approaches, and there are quite a bit of challenges when you use just a camera. One of them is that the cones that are really far away are quite small and pixelated. It's just like finite resolution camera, so you're going to have very few pixels per cone. The camera has a short baseline. This is also mandated by the rules, like because of safety of the car. And the car moves when it drives, right? And we found that the traditional 3D vision methods that might have been used, for 10, 20 years, based on some sort of feature detection, where you would detect the corners of the cones or something like that, they would be really range limited, because as you decrease the number of pixels, you can't really do this accurately, robustly. It becomes very noisy. You could do this with some sort of alternative 3D approaches. As Roman mentioned, for example, you could use the depth anything, monocular estimator that gives you a depth map for the whole image, and it's quite accurate. But that needs a lot of compute. It's really it's a large model, and when you want to run it in real time and process the data really quickly, it wouldn't work. Okay, so what could you do next? Maybe some of you are familiar with the perspective endpoint method. This relies on a known model of the object that you see in the image. So when you have the cone in the image, you have some of these cones in real life. You can measure precisely how big they are, like if they're 30 centimeters tall. Then you can find some of the key points or some features, and you could try to estimate how far and exactly where the cone is. But the cone dimensions are not guaranteed. They can change. There can be some small variations. And as I mentioned, the feature detection on these cones is very difficult because when they are far away, they're tiny, you have very few pixels. You wouldn't be able to tell with like 20 centimeter precision, you would have huge errors. So we need to do something else. To make it work with this camera, we needed something that's just completely out of the box and hasn't been used or is not being used conventionally. And what we do, we actually, I'm sorry, yeah. We just formulated this problem as like completely 2D geometry. We don't use any sort of like 3D conversion, no scaling. We just say that the world is basically an image because we don't care about like the Z coordinate. We don't care where the cone, if it's like 10 centimeters off the ground. Well, it doesn't make sense because it's always on the ground. So we just say, okay, around me here, like 20 meters, the world is just a plane, and there are some points on this plane. And when you have points on a plane, well, that's basically an image. And regardless of how you measure it, if you want to say like these cones are 10 meters in front of me, 5 meters to the left, it's just some sort of a special image. And when we look at the world as an image, and we have the camera image, we can start doing some clever, image-only geometry. In this case, it's a homographic transformation, so it's a 4.8 degrees of freedom transformation. And basically, all that we do is that we go from the image of the camera to the image of the world, and the image of the world happens to be exactly in like the metric coordinates that you need. So with just a simple 3x3 matrix, you like extract from the single image the exact cone positions that you need for the planning and for the localization. Okay, I will go back. First, you need some sort of detection of the cones, right? We discussed that classical features are not really enough. But what works remarkably well, even on the cones that are really small and really far away with few pixels, is object detection or just estimation of the bounding boxes. With modern deep learning models like YOLO, it is also very efficient. Like, right, they have like low millions of parameters. The computation is very quick, and they didn't have any problems detecting like the really tiny cones far away. So that's the first step. We detect the bounding boxes around the cones, and yeah, on our computer, as Roman mentioned, it's we have like an off-the-shelf computer, and even on that, it runs really quickly. You get actually like the detection of the cones is much faster than how quickly the camera can produce new images. And this has a big advantage of reducing latency, right? So when you receive the image, then you also need to take some time to process it and give the information to the rest of the system. This minimizes that latency taken by the detection algorithm. Okay. So we have the image from the camera, and what we obtain is this sort of local map. But as I mentioned, there is some sort of transformation, some sort of geometrical transformation that you need, and you need to estimate it in some way. So what we do, we build this sort of pattern of cones, and we exactly know where each of the cones is located, what are the exact metric coordinates. And when we take the image, we also know exactly the image coordinates. And then we use a completely standard least squares method to find the transform. So we obtain the actual like 3x3 matrix that for each point, each of the cones gives us its exact position in the world. It's like a very simple method, but you can see that it's incredibly accurate, like 5 centimeters of error. That's basically LiDAR territory. And we do that with a single camera and very simple transformation. But this is when the car is static, when it's standing still. When you start moving and the car starts shaking or runs over some sort of bump, you violate the assumption of 2 static planes. Yeah, this is also if you were to transform the whole image like the cones, what it would look like. It's a basically standard bird view image. Right, so when you start moving, the car is shaking, there's some sort of some bumps in the road, so the error grows. But when we've tested this against an actual LiDAR that was mounted on the car experimentally and drove around the track, we found that the difference between our camera system and the LiDAR system is actually quite small. Yeah, at around 15 meters away from the car, you are at about like 35, 40 centimeters of error, which is quite respectable given such an efficient and lightweight system. Now for the second block. When we have the cones, we have to build out the map, the track where we are driving, and then localize it within and know, what cones are ahead of us and where do we want to go. Mapping and localization is in this case like a completely standard robotics problem. Usually this wouldn't be solved in autonomous driving, like the modern autonomous driving companies, Tesla, Waymo. They don't really have to worry about this because the car is constantly moving. It's some sort of like dynamic location. It can't remember how the entire Los Angeles looks. But here, we are restricted to only some limited size closed tracks, some of the circuits that are maybe 500, 300, 500 meters long. So you can actually remember the entire track in some sort of like reasonable memory footprint, and therefore it makes sense to map the track because then you know more. You can remember all of the information that you had and allows you to drive more precisely. Because we only have the cone detections and the range is limited, we don't have like a 70-meter range of the LiDARs. We have like 20, maybe 25 when pushing it. It's difficult to have the SLAM really work robustly. There need to be some sort of heuristics, clever data association. So it's not completely trivial. There have to be some clever tricks. And we actually have two of these algorithms. We have an ICP-based one and EKF. If you're maybe familiar with these methods, I'll go over them individually. For the ICP SLAM, that's basically a iterative method that tries to align two point clouds. So when you want to localize in the track and you see some of the cones and you know that the entire track, you can just try which of the cones would fit on top of each other until you find the correct solution. And yeah, it's quite accurate. Actually, we found that we developed this diagnostic tool that allows us to track the car from a drone and like assemble what the real track and the real map should be, and also extract the logs from the car. And what we found is that it was quite accurate. We had a mean error in this case about 30 centimeters, which is almost state of the art when it comes to SLAM algorithms in Formula Student. So this is one of them, and the second one, the second one is the extended Kalman filter based. It's just like a textbook algorithm, and where we use it is that when we already know some of the cones, for example, when we've pre-mapped the track in a previous drive, or when it's the skid pad discipline, which, as Marko showed, the entire map is given by the rules. You exactly know where each cone is beforehand, even before you enter the track. So you can just hard code it to provide some sort of initial solution. And when you drive around, the tracks are built by people, so they are not perfect. But when you drive around, you can refine like this pre-hard coded solution, and you don't have to map the track completely. So that's where we use the EKF SLAM. It's a like really low noise algorithm. It allows for really stable and precise control. So you can push the car to its absolute limits, and that's why it's suitable for the skid pad discipline where we want to go really quickly and just on the edge of traction. Right, so we now have the cones. We know how the environment around the car looks like. And we have to plan some sort of paths to navigate the track, like to actually go around. We do this by planning first the center line, like the middle line of the track, and then we optimize it in some way that resembles how human drivers would want to drive. First, so we have the trajectory planner. This is a completely self-developed algorithm based on Delaunay triangulation. So it basically what it does, it finds the lines connecting the cones and then projects the cones to the center So we obtain like between each pair of the yellow and blue cone, we obtain a center point. And when you connect all of these center points, you have the center line trajectory where you can drive. So this sounds kind of simple, but because in some of the corners, there can be a really sharp corner, and you have a camera with limited field of view, so you won't see all of the cones. You might come to a corner, you might see I don't know, 3 or 4. And in the first lap, when you don't have the track already mapped, when you don't know the track, you're just learning how it looks, this could be a problem. So there are a lot of corner cases that have to be covered so that your car doesn't spontaneously just run out of the track. And what does this trajectory planner look like? So you can see the visualization of the trajectory in an image, and on the right is like the default metric coordinates. So you can see that it's the center line that goes between each one of the cones. Yeah. We actually developed an end-to-end method, which turned out to work quite well, but it didn't really, it worked really well for planning, but when there was like real world noise introduced, it could produce a little bit unstable results, less stable than like the analytical algorithm. So we still use this analytical algorithm. Fine, so now we got the center line, right? The center line, you have the largest margin to each side of the track. So if you were to hit a cone, you minimize this probability. There won't be any penalties. But driving on the center line is not really what you want to do. When you look at a human racing driver, they will have some sort of extremely specific curve that they will drive in each corner, so-called racing line. And they know that by driving this way, they maximize the velocity, the exit velocity of the corner, the shortest time that they have to brake, stuff like that. Okay, you would want to do this in the autonomous car as well, right? But how can you do this mathematically or procedurally? It's actually quite a difficult problem to like formulate and set up. So the way we do it is that this is just for illustration. We definitely won't go into the specifics, but it's just to show that this task that a human driver solves like intuitively just by looking at the track or just by driving around, we can exactly formulate it as some sort of optimization problem, right? Just define some sort of loss function as you would do with training a neural network. And you say, okay, I want to minimize this loss. And when you actually formulate the loss to reflect the incorrect trajectory or the suboptimal trajectory, you can use standard neural network training algorithms to find the minimum of the function which corresponds to the optimal trajectory, which gets you the fastest time around the track. So that's what we do. We formulate some sort of an optimization task, and then we optimize the path, right? Those are our parameters. The points of the track, of like the trajectory, and we find those that minimize this sort of loss. Right, so what does the path planning actually look like? This is the first pass when you do like the first plan of the center line. And then when you actually feed it into the optimizer, there is a very little difference, but you can see, for example, here in this corner, that it changes quite a bit. And so even though these adjustments might seem like really small and that they don't make much of don't do much of a difference, actually when you add them up and like from corner to corner, this can be huge. It can be like worth multiple seconds of time when you actually start driving. Okay, so we now have the trajectory that is optimal in some way, and we would like to drive along it. And again, we want to maximize the time. We want to be as fast as possible. So we have to plan or set the velocity of the car, like the speed you want to go, but you can't set it arbitrarily, especially not arbitrarily high, because there are some sort of physical limitations of the road, of the car, of the aerodynamics, stuff like that, that will give you some sort of upper bound on what you can actually achieve. So we again formulate this as some sort of iterative algorithm that for the planned trajectory, considers how sharp are the turns, right? If it's a turn or if it's a straight line. How are these turns like chained behind next to each other? And then you compute the maximum feasible velocity that you can go without slipping or just going outside of the track. And this works quite well, and you can see it here. When we indicate the speed as a heat map, you can see that the straights are the brightest or reddest to indicate like the highest speed, and you can see the car has to like gradually brake before coming into a corner, and then it again accelerates out. Okay, so now we know what speed we want to go along the trajectory, but we also need to know how to turn, right? You just can't go straight. So you need to compute the steering angle, the way to steer like the wheels to actually reach the corner or whatever is in front of you. And the method in this case is quite simple. You pick some sort of fixed reference point on the path in front of you, and you just say, okay, I want to go to this point. You can vary this based on speed, because when you're going faster, you might want to put it a little bit further, a little bit closer. So that is variable, and it's from the viewpoint of control theory, it's just a simple proportional controller based on like where the actual heading of the car is, that's the green dotted line, and the one where you want to go, which is the orange dashed line. So you would like try in every step you would want to go as close with the green one to the orange one as possible. And you can directly map this to the steering angle of the car, so the angle that you want the wheels to steer. Okay, and this is the last step. So now we know where we want to steer the car, and we know how fast we want to go. But the car doesn't take these values. Those are just some sort of like simplified physical values. And the last step is to like compute the actual, low-level control to move every wheel of the car and the steering wheel to get you to that point. How to do this? Well, you need some sort of torque controller, because our car works based on torque. So you request the amount of acceleration you want to have in every iteration, 100 iterations per second. And to actually compute this and like solve this control problem, you can define it again as some sort of optimization task. And a lot of care has to be taken in this task, because you want to have a differential drive. So that means you can't just set all wheels to have the same speed, same velocity, because then you would have problems in corners. So you have to brake or accelerate each wheel independently. And also, as Marko mentioned, we have a true four-wheel drive car, right? We have every wheel has this like completely independent motor, independent drive. So you can actually help the car to steer to the corner just by varying these forces that act on each of the wheels. And that can be also incorporated into the control problem. And this is solved like a standard optimization problem. And what you receive are 4 numbers, each telling you, this motor wants to exert this amount of force, front left, front right, and so on. And yeah, that's basically all of the core of the car, how you actually go from the camera image to the actuation command. And there are some nodes that we have, what we're working on right now, because of course those things already exist, but we want to improve, we want to do better. So as I talked about the vision algorithm, where we use the assumption that the surface is planar, sometimes it's not. Some of the circuits or some of the asphalt surfaces can be curved. There is no guarantee on this. And when they're like significantly curved and it's even like 5 meters in front of the car, it's already some sort of parabolic surface, the accuracy decreases because there's a large amount of error. So we are working on some sort of new vision algorithm. This also causes problems for the localization and mapping. That's also under development. And a big thing for us, and quite a popular thing in Formula Student, is optical ground speed sensing. which means that because when you want to measure the velocity of the car, like the actual speed that you're going, you have quite a few options. You can use GPS, but it is accurate, but it is slow, and it takes some time to catch the signal. You have to rely on some sort of external satellites, and then you can measure it from the wheels, right? How fast the wheels are spinning. That makes sense, but once you start slipping or you like push the pedal really hard, you put a lot of torque, you get slip, and the wheels are spinning much faster than what the car is actually moving. So that measurement is not accurate. And the ultimate solution that everybody uses is some sort of optical sensor where you basically take a camera image of the floor every 100 times a second or something, and you compute how much you moved in those 10 milliseconds to obtain some sort of speed estimate that's completely independent or external sources. Right, and this is us. A pustíme ten. And what we're going to play now is probably like the best drive of the past year. This was in Italy when there was a lot of rain, and we were actually the only ones. The only ones who were able to drive this, because everybody who used a LiDAR had problems with the rain. When you have rain, the droplets of water in the air, the LiDAR doesn't work because it detects all of these droplets as some sort of object, and there's a lot of noise. And yeah, basically everyone drove like a meter and then had to stop because their car wouldn't be able to navigate. And we had a camera, so we were completely fine. And yeah, we were able to drive like the entire 10 laps of the track drive discipline. Okay, so we'll just let this play here. And if you have any questions or want to ask anything, every one of us, please let us know.
Also, I think we should thank the speakers, right? All right, that was an amazing talk. Yeah, we are open for questions. If you have a question and you're online, just unmute yourself. We can hear you. If you are in the room, wait for me to give you the microphone. And since we have one, I need to hand back to whoever answers, right? So a little bit of overhead. I'm sorry about that. So any questions? Right, we have one in the room.
Like first question, are you limited by wattage that you can deliver? Is it like balancing what you give to compute versus what you give to wheels?
Yep, just wait a second, sorry. So, Marko?
The rule set limits us to 80 kilowatts, which we can distribute at one time. So the total sum needs to be below 80 kilowatts for the engines, but we are capable of going to 140 with the current setup.
Right, so like to answer that specific thing, no, we don't have to trade off between compute and like the motor power, because these two systems are separate, and the limits that Marko mentioned are imposed only like on the separate system that runs the wheels. So we could have like, I don't know, a 2 kilowatt data center in the car, and it wouldn't matter. We could do it. If we could do that, we wouldn't last very long, but yeah, we're not limited on that front. It's more of a, yeah, there's the efficiency category that Marko showed at the beginning. And I think like this energy consumed also falls into this category. Yeah.
The energy efficient only for piloted.
Yeah. The driverless car doesn't consider this, so you can run the 2 kilowatt data center, just you have to shut it off for the pilot.
Nice. Other questions?
What is the energy ratio between GPUs, CPUs, and the motor?
The energy ratio is we're now does whole autonomous system consumes for about 500 watts at max, and yeah, compared to 80 kilowatts, it's almost nothing.
Thank you. Right.
Yeah, I have a question about this specific scenario which we can see in the video, because there is a lot of noise from the drops of water. So did you have the track, model of the track recorded before it started raining, or it works even with this kind of noise?
Right. So in this case, we actually, because of this exact problem, we were worried to reuse the track from the previous run. So we let the car learn it completely from scratch. So in the first lap, I can scroll back on in the video and you can see it. When we start, there is actually no track, and we map it as we go, even in the rain, with all of the noise. Oh, right. Yeah. So this is actually by design. This is like the explicit loop closure. When you have a SLAM algorithm and you return to some sort of area that you've mapped previously, there is some sort of loop closure, right? The algorithm notices that it's seen these things before. And we do this explicitly when we see the finish line. So when we return to the finish line, we know that we've returned and we know that we've mapped it before. So we explicitly like adjust the entire map to match what we've seen along the way and correct it like to the final shape. It's like the mapping algorithm that's used to build a map.
All right. Any other questions?
You mentioned that you can drive autonomously or with a human driver, but you had to change something to do that, and that it took you like 5 minutes. Could you briefly mention what is happening if you're installing some system, or if you're just declutching something, or what's going on there?
I believe it was Marko who said that.
The main difference is we have to implement when we have the autonomous capability, autonomous steering. We have an actuator of the autonomous steering actuator, and we have to switch it off. So we have to physically unplug it. We have one screw which we unplug, and then it's disconnected, and driver doesn't go against the steering, because when it's plugged in and driver, it actually has a force that goes against him. He has to steer the wheels and the actuator. He could do it, but it will be harder for him.
All right. Any other questions? Sure.
My question is, if you have like different code for different modes, like
Yes, that's it. It works exactly how you described. We have a different code for each of the disciplines, and that is actually one of the strong parts of our system, because a lot of the other teams, they usually do this by changing just some sort of variable and having like all of these things hard coded. But the way Roman proposed the design originally is to split this into like separate code for each of the disciplines, so we can swap them basically on the fly, and it allows us to do a lot of experimentation. So we have like one .py file for the track drive, one .py file for the skid pad, one .py file for the acceleration.
Nice. All right. One more question.
Awesome. First of all, congratulations. Very impressive work. I was part of the founding team of eForce Driverless, and we did maybe 5% of what you guys are doing. So also, I'm very proud of how far you've come and of your achievements. But my question is, as the way I understand it, as you explained it, the car can be way more efficient and high performing once you close the loop and you can use the Kalman filter planning. So one way to improve performance perhaps could be to try and close the loop as soon as possible. So my question is, would it make sense, or have you considered using multiple cameras facing different ways, like for example, facing back, so that when you start your first run, you could already map out a little bit of the track facing backwards and maybe close the loop in the middle of the first lap?
Right?
Yeah, so well, maybe if like we could show or if you would see how like it works for the teams with the slam, right? So they have a slam that can see like 50 meters in every direction, and so they basically have this, right? So they basically have the whole map mapped out in the first 10 seconds of the drive. So in that way, we could put maybe a lidar or more cameras on the car, but it still would give us maybe like 20 meters in each direction, and the track is around like 150 in each way. We've considered it for multiple seasons now. We are always like, okay, we will finally get the second camera, get the third camera, but then we always realize, okay, we are actually bottlenecked by software, by our control algorithms, and so on. So yeah, maybe in the far future, but right now we are still bottlenecked by the algorithms and the software.
All right. Thank you. I think we have time for. All right. I actually had one question that I wanted to ask as well. Is for like these famous tracks around the world, there are the maps of the fastest drivers, like the optimal lines that you can download. Have you tried to compare your algorithm against any of these? Because I think there might be some differences. But...
First of all, the difference is that we don't race actually at the track. We're staying in the pits of the track. We are comparing them to our drivers. They can take the same track as we do, and there's still a lot of work to do. Like the racing track, the racing is great, but where we struggle is that the human brain is actually a supercomputer, and he can to every situation. So the line is just one part that we actually are taking a lot of similar trajectory as the pilots right now.
All right. Thank you. So let's thank the speakers again. All right. So as usual, we will post the recording on YouTube, and also the slides will be both on Meetup and YouTube. One more thing is that we already know the topic and the date of the next Mython AI Times, and you are all welcome to join us again. It's going to be on the 27th of February. It's going to be by Augustin Židek from Google's DeepMind about AlphaFold. We will again post the announcement on Meetup, so you shouldn't miss it. The only thing that I wanted to mention is that we might change the venue because we are barely fitting into this one right now already. We don't know yet. We will see. It's going to be in the invite. I think that's it. You are all welcome to stick around. There's beer on tap. There's refreshments coming. So thank you, and thank you guys for the amazing talk.